Hi, I'm Michael Dragalis with Confluent, and in this module, we're going to be looking at how stateless operations work in ksqlDB. Let's start by looking at the hello world of ksqlDB, creating a stream. A stream is a supercharged Kafka topic. In this SQL statement, I create a stream called readings. It has a schema of 3 columns, sensor, reading, and location, and their types are explicitly spelled out, string, double, and string. Notice that the sensor column is denoted with the key keyword. We'll look at what that means in just a second. There's also some additional metadata. We specify the underlying Kafka topic for where the data will be stored. We specify the serialization format, which in this case is JSON. And then we specify the number of partitions. When you're at the CLI and you issue this command to ksqlDB servers, what happens? What happens is that ksqlDB servers turn around and talk to the Kafka brokers. If the underlying topic doesn't exist, it gets created, and the additional metadata, like the types, gets stored in ksqlDB's object catalog. So in this case, I now have a topic, named readings, that has 3 empty partitions denoted by each of these numbers, 0, 1, and 2. Now that I have an empty stream, the next thing that makes sense is to put some data into it. I do that with rows. In Kafka, we have records. In ksqlDB, we have rows. The way that you get rows into a stream are with simple SQL statements, just like a relational database. If you've worked with Postgres or MySQL, this will be very familiar to you. I insert into the stream readings, naming the specific columns that I want to supply data for. Each insert statement corresponds to the invocation of a Kafka client producer call, and the data is stored in the underlying topic for the stream. Now, let's look at the representation of a row inside of a Kafka topic. Since each row is just a Kafka record, what does that record look like? When I look at the first row, I see that the offset is 0, meaning that it's at the beginning. I can also see that it has a key and a value, as every Kafka record does. Here the key is sensor 1, and the value is a map with a reading of 45 and a location of wheel. Notice how it got to be this way. Remember that the sensor column was denoted with the key keyword. That is why it ends up in the key position of the underlying Kafka record. This helps you exercise control in SQL of the underlying Kafka data. As you can see, we have more rows, and as I add more rows, they get added to the left. Now that we have data in our stream, what comes next? We want to do something with that data in real time. The simplest thing that we can do is a transformation. We'll do this with a persistent query, which is what we see at the bottom. What this query does is it consumes from the reading stream that we just created, and it selects a few columns. It selects the sensor and the readings, just carrying them through, and then takes the location and converts it to all uppercase. Just a simple little functional example. It takes this data and reads it indefinitely, and creates a new stream called clean. So we're cleaning up the data, you can imagine. And when you launch this program from your CLI to ksqlDB servers, it runs it perpetually and indefinitely. It's often running until you tell it to stop. What it's doing is that ksqlDB constructs a Kafka Streams topology to execute the query. You can imagine that we give this persistent query a name, PQ1, just to reference it here in this depiction. And imagine that this is a single server running a single persistent query. What it's doing is that it's sitting there waiting for new rows to show up and processing them as they arrive. This row, for instance, is from partition 2, offset 0, and the location is muffler. You can see how when it passes through the query, it's converted to all uppercase. As the rows are processed, you can see how ksqlDB tracks how advanced each partition is by the processed offset. These offsets are committed automatically for you through the consumer protocol. Let's do something slightly more advanced, filtering rows out of a stream. This shows how the programming model works. I take a stream, and I derive a new stream from it. I can chain these things together. This is the last query we looked at, PQ1. I'm going to create a new query, PQ2, again just for the purposes of inspecting it in this depiction, and this query will drop all readings that are greater than 41. When I play this out, the rows come in, and you'll see a few of them get discarded. This works because 2 persistent queries are compiled into Kafka Streams applications that are sharing a mutual Kafka topic. That is why the programming model is so flexible. This is particularly nice because you can group statements into whatever way you see fit. Here I take the 2 statements that we had before and I consolidate them into a single statement. You don't have to worry about where these things run. It's compiled down to the same semantic program, and that is the beauty of using high-level SQL. Because ksqlDB statements are executed as Kafka Streams topologies, you get all the guarantees you're used to with a Kafka consumer. Here's a look at how this would work with multiple persistent queries reading from the same stream. Here I have another persistent query chained onto the high priority stream. What would you expect if it were 2 Kafka consumers? You'd expect them to work in a conflict-free way. I'll play this through to show what happens. I have a row that comes through, and both persistent queries read it. You can imagine they're on completely different servers. Two copies of the data are created. They're completely separate. A copy here and a copy here. These queries don't step on each other's feet. You get the scale out that you would come to expect with regular Kafka consumers, and everyone gets their own isolated copy of the data.